Thank you, Kurt. Thank you for the invitation to honor Dr. Shiraz Tayabaji. It's my pleasure to be here and reflect on a few things that he's been doing over the years related to CRCP especially. It was beneficial to kind of, as I put this presentation together, to think back of all the things Shiraz has contributed to. Much of it has already been covered, so that's the great thing about being last. But then you're left with trying to fill in the blanks as other people cover what you were going to say. But as everyone else has done, I'd like a personal salute to Shiraz because as a young student at the University of Illinois, his name was well known, his work was well known, and it's always good to look up to people and their accomplishments, and it gives you a good goal to strive to do excellent work. And so I thought of three words that describe Shiraz: excellence in what he was doing. He always delivered quality work, whether that was written communications or design methods, and he was always committed. So once Shiraz was going to do something, whether it was a training course or a project, he was fully committed. You could count on him to do a great quality, excellent job. So those are qualities that I think all can strive for. It's great telling students this, but it's also great to see it in action. And Shiraz, particularly one of the founders of the International Society of Concrete Pavements, including all of his service and other organizations. He also was highly engaged in the educational mission of what engineers are doing and what they need to learn in order to adopt new technology. So I appreciate that about his career. Ever since I've known him, this has been about 30 years. I was a student at that time. He seemed to always be engaged in the educational part, as many of the speakers have said. He clearly was a leader in many aspects, whether that was professional organizations or leading conferences or technical societies, and being involved in developing standards and guidelines sets a great example of, you can know a lot of things, but at the end of the day, you need to be engaged in the end products. And those are the guidance documents, the standard specifications, and important to do that. And I've appreciated him doing that because it's helped me to see that those aren't just busy work, but important last steps. And I just wanted to have a few light statements here. One being, some of the lessons I've learned from Shiraz, very organized, very good at planning, very great communicator, and a few confessions that hopefully he'll forgive me for. One, he used to send coffee to Professor Thompson, Kenyan coffee. He probably doesn't know that Professor Thompson used to give it to me and I would drink it. And I was always excited to tell Professor Thompson to say, tell Shiraz to send more, because it was great Kenyan coffee and I enjoyed getting it from Professor Thompson. And secondly, Shiraz always stressed to have your presentations done at least a week in advance. Maybe, I think 25 years ago, it had to be ready 2 months in advance. And I'm sorry that I wasn't really prepared in advance again for this presentation, like always. So today, I want to just cover some innovation work that I'm more familiar with, and on CRCP as more of a challenge of what's going on right now with CRCP, particularly when it relates to these four main topics: structural design. We'll look at a few innovations in new and overlays, post-tensioning of CRCP. We'll then look at some material aspects that have been tried recently and how that's turned out in terms of internal curing, macrofibers, looking at behavior with various steel properties. And also then, is CRCP is a system behavior. How do we make sure our support layers, like any civil engineering structure, needs good support layers? How do we evaluate those and make sure that they're behaving in a way that's appropriate? And finally, as Shiraz spent a lot of time in the construction details are very important. So a few that that are interesting in terms of what we found recently about them, and Shiraz was involved in some of these as well, both with active crack control and terminal or transition joint designs. So I'd like to thank the Tollway, who originally funded a lot of the stuff that we'll see, and actually Shiraz was kind of a consultant for this project that provided feedback on this Tollway test section that allowed university professor types to build a bunch of different interesting test sections on a real live road. So that a lot what you'll see today is related to this Tollway test section. Now, one of the things about CRCP is it cracks naturally, and that's nice. There's no joints, the cracks are tight, but invariably you can have cracks that don't necessarily form in a very regular and desirable pattern. And I've listed, you see some here, divided cracks, cluster cracks, Y cracks. And so as we thought about how do you make CRCP perform better and last longer and not have premature failures, you really want to avoid kind of irregular cracking patterns. And so one of the things was during this, one of this recent studies was how could we use internal curing possibly as a way to produce better controlled and spaced cracks, both in terms of crack width and the crack dimensions or the slab dimensions. And so this was their original motivation, as well as making this a very cost-effective pavement type, because you need to deal with that relative to its service life. And so if you're not familiar with internal curing, which has been used a lot on test sections on bridges, it essentially is pre-wetted saturated aggregates, lightweight aggregates that are manufactured and expanded, and these porous aggregates are saturated with water as the concrete hydrates, especially at water cement ratios that are either below 0.4, or even if it's above 0.4, when you lose water to the external environment, the aggregates will release that internally stored water pretty easily because the pore sizes are so large. And that can help provide internal curing to hydrate the cement more. It produces a more uniform moisture gradient, so that can reduce curling, which was shown in some work we did, not necessarily for CRCP, but for jointed. And so this was one of the ideas that we were going to test out. We had Dr. Jason Weiss and Dan Zollinger on this project, and Dr. Weiss was an expert in this. So we were really excited to see how it could impact CRCP performance. Could it change crack spacing, crack widths, and performance? And so for this particular project, we just replaced the sand part of the concrete mix with 37% of the fine aggregate by volume. That's not weight. And so it's not a huge amount of replacement, but you can really, from the laboratory work, and even some field testing with slab curling, you can see a remarkable difference when you lose external water. Another thing that we tried on this test section, and I'll show the results of these when I explain all the factors we did, besides lightweight aggregates saturated, we also looked at active crack control. This had been originally looked at in the 90s by Dan Zollinger on some test sections in Texas. It was recent. We looked at it 20 years ago for Illinois Department of Transportation, where we saw cut across the slab with a soft cut. And recently in Belgium, they've cut notches in the side of CRCP. They were a little bit longer than this, so we built on what they did and did partial width, partial depth notches, about 2 feet long. And then we spaced them every 4 feet, hoping to propagate those cracks in regularly spaced arrangements early, as well as keeping the crack widths tight. So we'd like cracks to happen early so that the widths are distributed appropriately and not have dominant cracks that have very large movements or very large widths. And we really want to avoid the bottom left, where we have this clustering of cracks that can intersect and eventually give a premature spall or punch out that really has little to do with being overloaded or fatigued. But when you have too many cracks coming together in one location, you can create premature failures. This test section was located west of O'Hare, and it composed of 3 different test sections. For various reasons, they weren't all in the same exact location. Section 1, it was all our internal curing And section 2 was our control section. Section 3 had various other internal curing plus fibers, plus it was a little thinner, and it also had these active cracking. We appreciated this test section, but in all test sections in the field, you're kind of have to go with what the engineers are doing and just make some adjustments. So we didn't control everything we wanted to. We had several thicknesses, which wasn't ideal, but that's what we ended up getting. We had internal curing on 2 of the sections. We did active cracking on 1 of the sections. And the thing that really I want to point out here is the construction time and temperatures were very different for the 3 sections that were paved. 1 was paved, 2 of them were paved during the day. 1 was paved all night. One of them was paved at a fairly high temperature in the summer. Another one was paved in early spring at a very low temperature. And this will come back to probably cause some behavioral differences in some of the measurements we did. This is a cross section of the section. The CRCP was approximately 10.5 inches for the longest section. We had a base type that was a cement treated layer. And on top of that cement treated layer, there was 2 inches of asphalt on part of the sections and just a micro surfacing on several other subsections. So we did vary the interface that was directly beneath the CRCP. So we've been monitoring this over the past 4 years, and this was just published in TRB, what some of our findings. What you can see here is really the 3 sections, although they don't end up with the final crack spacing after about 4 years of monitoring. They're generally in the 4 to 5 foot range, with the smallest being section 3, which is the internal cure with the active crack control at every 4 feet. So that is varying pretty close to what the target was, which was around 4 feet. Note the internal curing, which shrinks at a slower rate than the normal crack. The control crack is slightly larger panel sizes, and but generally 1 to 2 meters are expected with crack spacings for CRCP. What's more interesting is the crack width analysis. As we look at the crack width out at 3 and 4 years, we find some interesting trends. The blue line there is the section 3 with the active cracking that was paved at a cooler temperature, and it's about 0.2 millimeters pretty much the entire time it's been monitored. And that's great. The cracks are very tight. We expect very good performance out of this section. This also has some macrofibers in half the section, further keeping the crack widths very tight. Internal curing had initially had lower crack widths and has subsequently had some higher crack widths. And there's some reasons for that. One being that it was one of the hotter days that this was paved during the day. And so anytime the temperature is really hot and then you have contraction from a very hot temperature, you're going to have larger crack widths, all things being equal. So internal curing, trying to control width, producing a crack width without controlling the concrete temperature, you have to do a little bit of both. It doesn't mean that internal curing can't have other benefits, but it's not a dominating factor in terms of only controlling crack width if everything else is the same. And here's section 1, the internal curing section. Typical CRCP crack spacings. You should be able to see those in the 3 different lanes. And this is what it looks like in section 3 when you have these active cracks here. You can see over here in the lane, and you can see how the transverse cracks propagate from them. So we've seen very good success with these active cracks. They're partial width, only 2 feet, so you don't have to saw cut much, and the cracks propagate across the slabs, and you don't have to saw cut. So this is really so we've seen very good results, very good small crack widths. And I'll show some more benefits of this active cracking. And one is that you see a lot of the cracks occurring early. You can see here with this chart, 71% of the notches activated in year 1. 85% of the notches have initiated a crack after the first 3 years. And of all the transverse cracks on section 3, 93% of them occur at a transverse crack. So you're not getting intermediate cracks, excuse me, you get them at notches. So you're not getting intermediate cracks. You're not getting these multiple cracks you see in some of the other sections, even with internal curing when you compare it with the control. And the fact that we're seeing the notches propagate these cracks early says it's a good idea. We're getting regularly spaced cracks. We're not getting a lot of random cracks, and that's good news for CRCP performance. If we look at the distribution of crack widths now, so if we measured all the cracks in these sections, some of these are several thousand feet long, we look at a crack width measurement in every crack in every section. Of course, you can have a mean value, which as I showed earlier, but these are the distributions of those crack widths. And interestingly, section 3 at the end there, the bottom right, very small cracks, very much more uniform and very low, whereas section 1 and 2, 1 being the with internal cure, section 2 being the normal, they still have this distribution of crack width, which probably is a result of the higher construction temperatures, plus the fact that we had other things going on, such as some undesirable cracks occurring. We did do some measurements, in fact, even at the end of the 4th year, and ironically, even the internal cure section had some crack widths at the time we did the measurements. The mean value was actually was higher than the control. And a lot of that has to do with, I believe, the cluster cracking that's occurring in section 2, which I'll show in a second, as well, again, as very high temperatures at construction. So a solution in innovation in CRCP like internal curing, you still have to pay attention to other good practices about paving at high temperatures. And I will say that really, all these sections are performing well. So despite my comments about crack widths, and that may not be good, we're just showing relative kind of measurements right now and not necessarily any distresses on these sections. But let's get back to the undesirable cracks again. You can see these various undesirable cracks. So let's compare these undesirable cracks from the various sections and see how internal curing performed relative to active cracking and then just the control normal paving concrete. And by the way, these were all slip formed with generally the same types of pavers and contractors. So what we find here is if we looked at Y cracks, first Y cracks, if I just jump back a slide, are number 3 here. Y cracks actually show the highest on the control section. Well, that's interesting. But we don't eliminate it with internal curing. Section 1, the black and blue, show less than the control, but don't eliminate it. So there's something there with curing and shrinkage and the rate of shrinkage that seems to be helping with internal curing. When we go to complex Y cracks, which are related, what complex Y cracks would be number 1, where you have some clustering and a bunch of cracks that kind of come off other cracks. You see, again, we've reduced those significantly with internal curing and active cracking for that matter. That's the blue. Divided cracks, again, same conclusion. We're not eliminating them, but getting them very small relative to the control. That's all good news. Now we get to cluster cracking. When we go with internal curing, notching the slab, we actually eliminate cluster cracking, which is Shiraz and Dan Zollinger had come up with a way of defining cluster cracking, and that's what we use to define cluster cracking in this project. So good news is cluster cracking can be, or a lot of these undesirable cracks can be minimized, some eliminated with internal curing, with good partial width, partial depth cracks notched at the side, and that bodes well for premature distress on CRCP. So that kind of wraps up the Tollway project. Part of the Tollway project were other innovations, and Dan Zollinger came up with some ideas on post-tensioning CRCP. In the transverse direction, your tensile stresses are the highest in CRCP. So his idea was to actually come up with a way to transverse post-tension a CRCP section, reduce that lateral stress by compressing the slab in its width direction with solid bars that have plastic sleeves around them. And so we built some test sections in Victoria, Texas to do this. The verdict's still out on this, but the concept again, Dan Zollinger has a report on this as part of the report of our Tollway project. That there's some value here in post-tensioning CRCP. You do get a thickness reduction. The question is, how do you can build this efficiently and get the tensioning you need in the transverse direction? So these test sections exist. I'm sure Dan's going to continue to monitor those. Now let's jump to support layers, which sometimes you're kind of left with, if you're building a new pavement, you can pick your support layers. Sometimes you'd prefer not to move the support layers around and use other recycled material on the job site for the support layer. So how do we assess whether a support layer is acceptable, both in terms of its erosion resistance, as we heard from Julie in the last talk, its friction, its composite action. And we know asphalt's been really good under CRCP. And if you have if you can spend as much money as you want to build CRCP, you can build thick, dense graded asphalt under CRCP and it does well. But what about in these reconstruction projects where you have recycled materials available, recycled concrete, or you have, it may be cheaper to supply a cement stabilized layer beneath it. What can I do to evaluate whether these are going to work without building tons of test sections? And one thing, this data comes from our Tollway project, is one thing you can do is evaluate existing CRCPs and look at how well some of the different base layers are providing composite action and friction. In this case here, we have the CRCPs on the Tollway section, and this effective thickness here is kind of the concrete thickness plus the base thickness. Concrete thickness is around 10.5. The base can be anywhere from 4 to 6. But it's a lightly cemented base, and you can see that effective thickness makes the slab behave like it's somewhere in 13 and 14-inch range, which is pretty good when you think about normal truck traffic. You're not going to need much more than 12 or 13 inches of total CRCP thickness. This is behaving like it's much thicker because of the nice support, friction, and the stiffness of the underlying base layer. The other thing that's super important that was alluded to in the last presentation is erosion. And Dan's come up with this nice Hamburg wheel testing idea that you can look at. You can evaluate the erodibility under the Hamburg test, which is primarily used for asphalt permanent deformation under higher temperature tests. But under this action of higher temperature and water and a rolling steel wheel, which you can see here in this middle section here, you can evaluate the erodibility of a base layer that's maybe too lightly cemented, or a recycled mix that's been cemented, and come up with a criteria that it would be acceptable under CRCP, which are going to have higher deflections than a typical jointed section due to the closer crack spacings. So this Hamburg device, definitely a good idea to look at the stability of alternative base types under CRCP pavements. And my final topic is really talking about what's going on with CRCP overlays. We can talk about building brand new CRCP, but really a lot of existing roadways already out there, and really the options are asphalt overlay, concrete overlay, reconstruct. And so the good news is a lot of experience with CRCP overlays, not just in the US, but all over the world. So engineers that are listening, there's a lot of information. The new overlay guide that'll be coming out here any time now, probably in April, from CP Tech Center, will have a chapter on CRCP overlay. And you can look this up and look at some of the references. Illinois, where I live, has good experience with 7 major projects with CRCP overlay, the last being a project in more southern Illinois. Obviously, a lot of these overlays are in more rural areas where you can have a lot of freedom with the grade, the shoulders, the ramps, not many bridges. But it's a very viable option, especially in states where you have a lot of traffic. And you want low maintenance and long life. And the life cycle cost on this, if you look at a 30-year, 25-year period even, will show CRCP overlays are a great choice. And one of the things we're seeing in Illinois CRCP, some of the ones built in 1995 have very great ride quality, very high condition rating numbers, and very thin 9-inch CRCP over an existing jointed reinforced. It's 26 years old. This is going to last 30 years, no problem. Even some of the ones in the early 2000s, again, very high condition ratings, very low IRIs on those sections. This is one of the heavier travel overlays that were done in Illinois in I-70, a big truck route going through Illinois. And one of the ones I was involved in about 8 years ago was down in the intersection of I-57 and I-64. And really, this has a slight twist where the existing roadway had a lot of punch outs and durability cracking and very distressed. So could we do something other than just overlay with CRCP or do a total reconstruction? And what was found is for the majority of this section, or a large part of this section, we could rubbleize the existing concrete, put it in the layer down, and then build a 10.5-inch CRCP over that to provide that long life, low maintenance type concrete roadway. And that was what IDOT chose. It turned out to be a 10.5-inch section. Like I said, they did do some reconstruction on some sections with 12-inch CRCP. But this primary project, the difference was the overlay was on a rubbleized concrete and not what's traditionally done. You rubbleize the concrete and then you put asphalt on top of it completely. And this is a picture of that where you have the inner layer of asphalt here, your black steel, and your overlay material. Your existing CRCP is obviously below both of these layers. And just a couple other things before, as I wrap up. California has really got into overlays now. They have 2 projects built. They're building these on jointed plane concrete, so they're overlaying existing jointed planes with relatively thin CRCP in pretty heavy truck routes in Southern California. And that's in this upcoming CP Tech report. Oregon's another special case with studded tires. A lot of their interstate that they built out of asphalt had worn out wheel paths, so they started overlaying with their asphalt interstate highways with CRCP, and had very good performance, very good ride after more than 20 and more than 30 years for some of these. And they recently built another one of these sections over asphalt in 2017. Nope, I said I was in, but one last thing, terminal joint movements in CRCP could be a problem. These where the CRCP comes up against a bridge or an existing roadway of a different type, could be asphalt, could be jointed plane. So the CRCP has a lot of movement at that end. And Shiraz came up with some new ideas on this transition slab detail, and that was actually implemented at the Tollway. So these are very complicated to construct. Kudos to Shiraz for coming up with a new idea around transition slabs that are easier to construct, kind of limit the movement at those joints so you can seal them. And so these details are important. And I know we're almost out of time here, so I won't read my summary, but there are innovations. Shiraz has been involved in a lot of innovations. I'm sure he's going to continue to be engaged at slightly less commitment time, but it's exciting to be part of his journey and see what he's done in his career. So thanks, Kurt.